Hello everyone, today is lesson 12 of the bootcamp and I would like to show you a few things and to wrap the chapter for web services. And the thing that I would like to show today is about databases. Last time, 2 weeks ago, we covered how to talk with databases using Entity Framework. And in fact, we didn't really learn much about databases. The things that we did were mostly related to ORM and the magic around it. We didn't really learn to work with databases by itself. We just use a tool that helped with it. But today's lesson is to understand what happens under the hood. How does it really work and what we need to do? So let's get to it. As a reminder, in the last lesson, we generated a SQLite database from our models that we created in previous lessons. So this is the database. It has items and shopping lists. And from those, we created we had these two models right here. Oh, I should delete this. Okay. So we had these models, and from these in here, basically by writing these 3 lines, we were able to generate a database out of them. So as a reminder, DB context is an abstraction on top of database, and DB set is an abstraction on a table. But what does that mean in database terms? So a database is this whole thing that you see here, and it's made of multiple things. A database can have functions within itself that you can define just like you would define functions in your code in C#. A database obviously has data. Data is stored in tables. Tables are made of rows and columns. This is a column. It has a type and a name, essentially 2 things. And on top of that, it has a bunch of properties per se. For example, my ID mustn't be null. Other things must be unique, and so on and so forth. And some things refer to other things, and so on and so forth. So tables are made of columns and rows, and here we can see columns, and here you can see rows. Columns up there and rows down here. So this means that a single row is very similar to a single object in OP. It's just a single instance of a table, you could say. So when you apply some values to table columns, you get a row. And yeah, that would be the essence of it. And there are many different SQL providers. For example, right here you can see SQLite, and SQLite is mostly used for Android or local databases, local storage, since your apps of your phone need some storage. And it doesn't really need to be a big server, something expensive or remote. You don't always have to have that. Well, when you don't need that, SQLite is a perfect choice. SQLite is a perfect choice because it's lightweight, it's simple, it's easy to set up, install, and use. It's very much like a file. My database literally is right here. It's just a single file, but it has structure. And that's why databases are useful. They give data structure. They are not unorganized. They're very organized. And that allows us to look up for data, insert data, update data extremely fast. Using a database is the fastest way of updating data that there is, updating or getting, just working with data altogether. And that's why we need databases. If we didn't have databases and just used normal files like text files, CSV files, JSONs, etc., we would be spending days for what now takes seconds. That's why we use a database. Going back, we already have some examples that I've shown. And it's important to say that this is SQLite, but there are other kinds of databases. There is SQL Server, there's MariaDB, there's PostgreSQL, there's MySQL, and there's CassandraDB, and so on and so forth. There are tons and tons of database providers, and you might wonder, but why? Well, SQL by itself is just a baseline, and all those different DB providers have built on top of that baseline, creating a very solid experience for their niche use cases. So they supplement baseline SQL with their niche use cases. If you are a beginner, you might not even notice differences between all of them. But when you go into details and you use the most out of the database provider that you have, then you start noticing big differences about different kinds of databases. All of the databases mentioned so far are SQL. And SQL databases are called relational databases. Anyways, we will not cover differences of different providers. It's not that important. If you understand one provider very well, understanding some other provider should be very easy. It's just a different dialect of the same language, essentially. When it comes to SQL, not SQL, but table structure, it's worth mentioning that tables, they usually have a separate column for ID, like you see here. And ideally, a single row should be identified by a single identifier column. So I could potentially identify a person by their living place, name, and surname. Like just combine those three things and identify a person. But it doesn't work for all scenarios, and it is slow and complex. Compare just using a single field as opposed to using three fields for getting a single person. And of course, it's faster when we filter on one thing rather than filtering on three. When it comes to ID fields, they're usually either long or integer or GUID. There are basically those three types of IDs. And long and int is useful because it can be auto-generated. Int is usually used when we think the table will be small and there is no risk of running out of ID values. Long is usually the usual choice for ID because tables grow enormously. And lastly, GUID is good when we want to merge two databases that have the same structure, to merge data into the same tables. So then if you have GUIDs, you avoid conflicting keys, and that's why it's useful. If you have ints or longs, the data will be conflicted inevitably. And you will need to manually do the importing. Cool. And all that you can do in a database really comes down to 4 operations. It's create, read, update, and delete. And if you take every letter, first letter from these operations, you get an abbreviation called CRUD. So CRUD is what databases are for. And it's really easy to execute SQL. It's very intuitive. It's like almost a pseudo kind of language because it reads like English. So, for example, if I want to get all elements from table items, I can simply write select all from items. And you can see the data is here. If I want to select all from shopping lists, I can write select all from shopping lists. And you can see my shopping lists. The star symbol here, the asterisk here, symbolizes, well, means getting everything from this table. So it's super simple syntax. Of course, I can specify what I want to get. For example, I want just shop name and address. And you can see it returning simply what I asked. I can even alias things with simplified names. For example, instead of shop name, I think it's redundant, and I'll simply say it's a name. So here you can see I renamed a column as I wanted. You can order data. For example, I will order it by name, and I'll specify that it will be descending order. And you can see that the two flipped in the order they were returned. So there's a ton of things I can do. If I want, I can combine these two. And for example, I can select what items come from what shop. And I can do this with a join. So if item has a matching shopping list ID, I take data from item and connect it to the shopping list. So we can say items dot name as item name as shop, or just item. Yeah. So if I do this now, you can see I got all the items from all the shops with all their names. And it's really intuitive, simple, and easy to use. It needs a little bit getting used to, but when you understand the gist of it, you'll be just fine. Left join is exactly the same as inner join, but it has a single exception. For example, let's go to data and let's say that this item has, okay, I won't be able to do that. But because it has a constraint, so it's impossible to set it to null. But sometimes columns can have a foreign key null. Foreign key, by the way, is this, and private key is this. So private key identifies a single row. So for example, I can write where ID is 1. So it will get me item of ID 1, and I can trust it will be just one item because I filtered on ID. And foreign key is used to connect two different tables together. Main table is the one that has a foreign key, and child table is the one that has a primary key that that matches that foreign key. So this combines two tables using this condition. So when shopping lists ID matches items shopping list ID, we connect the data from the two tables, as you can see here. So it groups it nice and easy. Cool. And that's select, that's filtering. Let's move on. So this is a get, or read rather. If we want to create something, and what I'm writing here is a comment, by the way, we can do insert into what table, into, let's say, shopping lists. And then we can say what columns are we inserting. So I will check what columns does it have. Shop name, address, is progressive taxes, fixed taxes. Values, and then I specify what values. So that's shopping, shop, then address, non-existing, let's say, is progressive taxes. True. Fixed taxes, 10. Let's run. And let's see what it says. Result query executed successfully. So if I select all the shopping lists now, you can see I just inserted another shopping list right here, test shop. So this is how you can do a create. Create and read are two really non-risky operations. If you mess up, you won't really see any impact. But now starts two risky operations, dangerous operations, called update and delete. So with update, we require a table. What table do we want to update? So I'm updating shopping lists. What do I do with shopping lists table? We will set, let's say, fixed taxes to 1.011 to a shopping list of ID 1. If I run this and select shopping list of ID 1, you can see the taxes that I've just applied. Very simple. When you are unsure how many rows will be affected, or to double check that it's indeed just one row, you should always, before doing a update, write a select. And see how many really rows will be selected. So a single row was selected, that's the value I want to update. I'm happy about it, I will execute it. So you can see that it worked, so it's great. So we have create, update, read. Read is obviously here. So create, read, update. And lastly, we have a delete. So all we need is to say what table. Shopping lists. And specify ID. So we will delete the last record. So test shop will be deleted now. And if I select, you can see there are only 2 tables now. Sorry, 2 rows now. Cool. So that is delete. And why is delete and update scary operations? Because if you do forget this where condition, you will potentially affect rows that you didn't want. And that's why I recommended always running this to see whether the row you're deleting affecting is really the right row. It's a nice way to double check. So that's a very basic create, read, update, and delete. And for a beginner, like for someone who's just starting a career, that's probably enough. You might be asked to do a union. So a union is basically you take 2 tables. So we have 2 selects, for example, where we select shopping list name from one and item name from another. So for example, like this returns 2 and this returns 11. So with union, given 2 tables have the same column names, and indeed this table has a single column name, like this result has a single column named name, and this one also has a single column name. And if I do a union, it will connect the values from 2 tables into one. And yeah, so you can see there's a bowling ball, and there are those 2 other values. It didn't show duplicate values because that's how union works. It excludes duplicates. So yeah, cool stuff. And that's pretty much all. Let's see what else. In searches, you're often asked to find something that isn't exactly as you type. For example, the start matches, the end matches, etc., etc. So we can do that using a where and a wildcard symbol. So let me select all shopping lists. That start, and that start is done using a like symbol, and a string filter is done using single quotes, and a %sign is used for a wildcard symbol. So it says basically the start can be anything, but it has to end with duper. So super space qualifies because super space is followed by duper. So if I run this query, Result near syntax error at line 37. Select all from shopping lists. Oh, I forgot the column name. So shop name. Let's run again. So you can see it returned that single row. Full stop, very simple. Wildcard. And again, if I type super here and then this, I will get the same results as well. But if I mess it up and type something like this, it will no longer find it. That's cool. Let's continue. When we have rows and tables, it's also quite important to remember that by default, let me modify table. Yes, cancel. Modify table. Come on. Okay. So here, as you can see, there is this foreign key thing. So if I double click, it allows me to choose what this column refers to and which column in that other table allows me to connect the two. And usually the relationship between two tables is that a column called table name ID is a foreign key, and within that table, an ID key will be the primary key of that table. So like this, we link two tables together. And the cool thing about this is this delete cascade relation, rule more like. So if I delete a single shopping list, sorry, if I, if I delete, sorry, if I delete, if I delete a single shopping list, items of that shop will be dropped as well because it says delete on cascade. So we can test it out. You can see there are 3 items here. So if I delete shopping list 1, the items should be dropped 2. If I run this and select everything once again, you can see that, well, that's actually a bad example. Let's see, items. You can see that there are no more items at shopping list 1 because deleting shopping list with ID 1 also deleted all the items. And that's what cascade delete rule does. If I delete the parent entity, that means that all child entities will be deleted along with it. So that's a small rule. In SQL, tables have relationships. We already witnessed that. And when I have a foreign key to another table, that kind of, and if the other table doesn't have a foreign key back to my table, then that relationship is called a one-to-many relationship. And this kind of relationship that item and shopping lists has is the most common relationship in SQL. There's also a one-to-one relationship where primary key of one table refers to primary key of another table. And it's not a very common relationship. It's an inheritance kind of relationship, but I wouldn't recommend using it. I still think I like you don't really need this normally unless you have many tables that reuse the same fields. But that's rare. That's pretty rare. We don't use inheritance that much in modern programming. It's more about composition. But it's okay-ish, but it should be like double, triple reconsidered. And so inheritance is one-to-one relationship when one primary key refers to another primary key of another table. That's one-to-one. And when two tables cross-reference each other, that's called a many-to-many relationship. And we don't want those at all. And we fix those by putting a table in between. So in the wiki, the example I give is that a single book can have many co-authors, and a single author can be of many books, can offer many books. So books, how do you feed many authors and how do you feed many books to those tables? You cannot really do anything. But if you put a table in between them, like so, then, by author ID of this book will reference this book author, and then book ID of this author will reference this guy, and that way you can see already it's a very familiar relationship. It's a one-to-many relationship. So by adding this in-between table, we have just created two one-to-many relationships and eliminated what was otherwise a many-to-many relationship. And it's useful for that reason, because it would, like, by adding a single book, we would need to add also, we would also need to update an authors table, and that's just not viable. But like this, we can independently manage the two. You don't need to worry about this if you're working with an ORM. It will be handled for you. What's the flow of inserting data into a table like this? Well, I think I messed up. This doesn't refer to that, and this doesn't refer to that. Yeah, I messed up, sorry. So, as you can see here, there is no reference to anything, and here there is no reference to anything. So you can add books and authors independently, and when you want to make a link between the two, you simply add it here. So by adding this intermediary table, you allow fixing that problem. So bad, it looks like this. And good, it looks with a third table in between by moving these two in this one. Okay, so that makes it one-to-many relationship, and that solves the problem. And the last thing I wanted to show is entity framework database first approach. So last lesson we generated this database, But imagine that we didn't generate this database and we started by creating tables. And it's very simple to create tables and things like that. Like, I literally don't need anything at all whatsoever. And like, that's it. I created a table. It's very easy, intuitive. If you're using a database management tool, like I do use DB Browser for SQLite, you like each tool works differently, but they all are kind of intuitive, so I won't explain much about this. But you can also, as you can see here, see SQL that it uses to generate these tables. So you could also use SQL. SQL is more intimidating to create tables. So as a beginner, I recommend just using a tool like I do. Anyways, make sure if you want to generate database models that we have here, make sure you have this package installed, Microsoft Entity Framework Tools. And this allows us scaffolding database. And what that means is converting database into models. So if I copy paste this into a command line, sorry, wrong tool. It goes to my database, and we already know what database am I using. I'm using this one. And my provider is the one that we have NuGet packages with SQLite. So you need to provide that too. And finally, you need to specify where do you want to put your models. And I want to put my models in db/generated folder. And finally, you need to specify the project that you're using for this. And my project is shopping list API. Like, to which project should the files end up to? And if you specify everything correctly and hit enter, shopping list API. I misspelled shopping list. So it builds the project and tries to generate stuff. And you can see in here, a folder appeared, generated. And you can see something very similar that you made yourself a while ago. But this is actually what SQL does under the hood. Not SQL, but Entity Framework. It takes this database and builds models out of it. That's really all. That's as simple as that. Do you have any questions? In the meanwhile, as I wait for this answer, I will commit this. Just this. And yeah, I can close this. It's not needed. And I will update this as well. We won't need this as well. Okay. Yep. So edit clarification for SQL relations. Push. So if you want to read more about this, there's a link to the wiki where I pretty much what I explained live, I've written in text. And yeah, after this, you should have a really solid baseline of how to work with databases and just proceed from there and Google up what you want specifically for your assignment. But this gives you a decent understanding for what is what and how to work with SQL. So thank you all for watching this lesson and see you probably next month where we start front-end lessons. So see you and take care.